Okay guys, so here are your notes for P.5, rational expressions. We've got our objectives. First, we're going to find domains of algebraic expressions because that relates directly to when we're going to be talking about rational expressions. And then we're going to be working with rational expressions, simplifying, add, subtracting, multiplying, and then we're going to be working with complex fractions and difference quotients. So to start things off, let's fill in these blanks. Domain of an algebraic expression, the set of real numbers for which an algebraic expression is defined is the domain of the expression. Two algebraic expressions are equivalent when they have the same domain and yield the same values for all numbers in their domain. So finding the domain of an algebraic expression. So remember, the domain is what x cannot be. So what x cannot be equal to. So remember, we cannot have a negative under a square root, and we cannot have a 0 in the denominator. Other than that, everything else is defined. So if you don't have a square root or an even radical, and you don't have a fraction, then your domain is going to be all real numbers. So for part A, this is a polynomial, more specifically a cubic. There is no fraction, so no denominator we have to worry about, and there are no radicals. So our domain is all real numbers. All domains of polynomials are all real numbers. Another way we can write all real numbers is from negative infinity to infinity. The domain includes all of the numbers on x. So all the way from negative infinity to infinity. Now on part B, we do have a square root. So we cannot have a negative number under the square root because it will not yield a real number for us. So we know that the quantity under the square root, the radicand, so x minus 2, has to be greater than or equal to 0. It can be 0, but it can't be negative. It has to be non-negative. So we're going to add 2. So x has to be greater than or equal to 2. Now, we just talked about a couple sections ago putting this into interval form. So we're including 2, and we're going all the way up to infinity. Now, in part C, we do have a fraction. So remember, we cannot divide by 0. We cannot have a 0 in the denominator. So x minus 3 cannot be equal to 0. So we're going to add 3. So x cannot be equal to 3. So previously, we might have stated that the domain was all real numbers except 3. Except x equals 3. But now, since we're in college algebra, I want to elevate our vocabulary and elevate our notation. So we're going to use interval notation. So from negative infinity to 3, but not including 3, we're fine. And then from 3 to infinity, we're fine, but not including 3. That's why I use the parentheses. So we join them with what's called a union. And a union basically just means and. So this would basically just mean, hey, at 3, we can't have a value there. There's going to be either a hole in our graph or an asymptote in our graph. So you guys pause me and try. On A in the try, this is a polynomial, and normally it would be all real numbers, but they restricted the domain for you. So basically what they did was they took this polynomial and cut off some of the graph. So they just told you the domain basically. So your domain is from 0 to infinity. On B, x plus 7 has to be greater than or equal to 0. So x has to be greater than or equal to negative 7. So from -7 to infinity are the x values that our graph will hit. And then finally on part C, we know that x cannot equal 0. So if we put this in our interval notation using our union, from -infinity to 0, but not including 0, we're fine. Then from 0 up to infinity, we're fine. And domain is so important before we get to rational expressions because rational expressions are fractions. So we're going to have denominators we're working with, and we're going to have restrictions in those denominators since those denominators cannot be equal to 0. So that's why domain was so important to talk about. The quotient of two algebraic expressions, such as part C, is a fractional expression, otherwise known as a rational expression. We spent a lot of time on this in Algebra 2. So today we're going to just review it and go a little bit deeper. So recall a fraction in simplest form. A fraction is in its simplest form when its numerator and denominator have no factors in common. So like 5/7 is in simplest form, but 2/10 is not, because that is able to be simplified. To simplify a rational expression, we're going to divide out common factors, just like you would a regular fraction. So with rational expressions, we always factor first. So that's why P.4 was so important, because we reviewed how to factor. So in a lot of these, I'm going to skip the factoring process just to keep the video time down. You guys can look back on P.4 on how to factor some of these. So, simplifying a rational expression. First things first, we really need to factor the numerator and factor the denominator. So if we factor the numerator, it's x method, so it's going to be 2 factors of -12 that add to 4. So it's x plus 6 times x minus 2. The bottom, we have a GCF of 3, so we have 3 times x minus 2. Now, before we start dividing out, we want to state excluded values. So remember, x cannot be 2. Since we have an x minus 2 factor in the denominator and an x minus 2 factor in the numerator, we can reduce, and our final answer is x plus 6 over 3. X cannot equal 2. So if you would graph this on Desmos, it would look like a line. But if you would zoom way in to x equals 2, there would be a hole here because of the restriction of this factor, x minus 2, in the denominator. So pause me and try B. But this is how B factors. 4 times x plus 3 over x minus 6 times x plus 3. Our restrictions are x cannot be 6 and x cannot be -3. Because if x was 6, it would make this factor 0, which would make the denominator 0. If x was -3, it would make this factor 0, which would make the whole denominator 0. So after we've listed our excluded values, we can reduce, and our final answer would be 4 over x minus 6 with these excluded values. So don't forget to list original restrictions. So we don't wait till we have our final simplified answer to list restrictions. We do it with our original factored answer. So once you factor the original problem, then you list restrictions. All right, let's do some that are a tad bit harder. So for part A, I'm going to pull a negative out of the numerator and flip this around. So if I pull a negative out, I would get x squared minus x minus 12. And then in the bottom, I still have 2x squared minus 9x plus 4. Now I'm just going to go ahead and factor top and bottom. The top is X method, the bottom is AC method, or what we call rainbow method. So if you need a second, pause me and factor this. So the top would be, we still have this negative out front. We have x minus 4 times x plus 3. The denominator factors like x minus 4 times 2x minus 1. So remember, before we go ahead and reduce, I need to state restrictions. So x cannot be 4. Remember, this is how we do this. This whole factor cannot be 0. So then we just isolate the x. So 2x cannot be 1, x cannot be 1/2. So x cannot be 4, x cannot be 1/2. Once I have my restrictions, I can go ahead and reduce, and I get negative x plus 3 over 2x minus 1. Go ahead, pause me, and try part B. Your answer should be negative 3x plus 2 over x plus 5. X cannot be negative 5, and x cannot be 1. Remember, if this video is going too fast, please pause, go back. If you need more time factoring, take time factoring. Look back to P.4, that was our section on factoring. Just to keep the video shorter, I'm gonna not show that step since we just learned that lesson. So operations with rational expressions. Multiplying. Remember, we first simplify, and then we can just multiply straight across. To divide, we multiply by the reciprocal. And remember, we said keep it, flip it, change it. Keep the first, flip the second, change the sign. To add and subtract, remember you need common denominators, which we're going to do a bunch of examples. So first you need common denominators. With adding, after you get common denominators, you just add like terms in the numerator. With subtraction, remember, sometimes you have to run that negative through. So it can sometimes get a bit tricky. So with simplification, remember, when you factor, you can reduce with something in the top and something in the bottom. As long as one of the factors is in the top and the other factors in the bottom, we can reduce by them. So, in this problem, I need to factor every single piece, both my numerators, both my denominators. So my first numerator ends up factoring like this after I use AC method. My first denominator ends up factoring like x plus 5 times x minus 1 after I use x method. My second numerator, first I have to pull out an x, and I get x squared minus 3x plus 2. And then I can use x method to factor this piece. So x minus 2 times x minus 1. And then the second denominator is just straight GCF. So I can pull out a 2x, and I'm left with 2x minus 3. So remember, x cannot be negative 5. X cannot be 1. Don't forget about the 2x. X cannot be 0, because if x was 0, that would make this denominator equal to 0. And then x cannot be, if this piece was equal to 0, 2x minus 3, we would get 2x equals 3, divide by 2, divide by 2. X cannot be 3 halves. So there are all my restricted values. After that, I can go ahead and start reducing. So I see an x minus 1 on the bottom and an x minus 1 on the top. I see a 2x minus 3 on the bottom and a 2x minus 3 on the top. Then I see an x on the bottom and an x on the top. After I think I'm done, we multiply the numerators straight across. So I'm left with x plus 2 times x minus 2 over 2 times x plus 5. So pause me and try this problem. But this all factors like 5x times 3x plus 1 over x times x minus 6 times x plus 3 times then we factor the next numerator with x method. So x minus 5 times x plus 3. And then the next denominator is with AC method. So x minus 3 times 3x plus 1. So before you go crazy and start crossing things off, remember to list your excluded values. So x cannot be 0, x cannot be 6, x cannot be negative 3, x cannot be 3, and x cannot be negative 1/3. Once we've done that, we're looking for factors that are in the top and bottom that the top and bottom have in common that we can reduce by. And I see an x and an x, so I get 5 times x minus 5 over x minus 6 times x minus 3. All right, dividing rational expressions. So the only difference with dividing is we keep it, flip it, change it. So we're gonna flip the second fraction and change the sign to multiplication. So on part A, we flip this fraction. Now, this is a difference of 2 perfect cubes. That's where we do the x cubed minus 8. We break down the first term. So we get x minus 2 times x squared plus 2x plus 4 over x squared minus 4 times x cubed plus 8 is really similar to x cubed minus 8. It's just x plus 2 times x squared minus 2x plus 4. And then x squared plus 2x plus 4 cannot be factored. We can, however, factor x squared plus 4, and that is x plus 2 times x minus 2. So we know that x cannot be 2 and x cannot be negative 2. This will yield us no 0 on the bottom. So now we can go ahead and reduce. And I get x minus 2. Oops, never mind. I don't get that. All I am left with is x squared minus 2x plus 4. For part B, another way that you can express a division sign is by a fraction bar. So part B just looks a little different from part A, but it's almost the same. It's just x cubed minus 1 over x squared minus 1 divided by x squared plus x plus 1 over x squared plus 2x plus 1. So after rewriting that, you guys try it. Pause me and try it. Your answer should just be x plus 1. That's how it simplifies. So I think I'm going to end this first video here after division. So go ahead and try the problems in your homework that you can do. And then I'll be back with a new video starting with example 6.